Hi ladies and gents, let's start with our D1 preparation. I'm planning doing a series of videos which will go over all of the chapters of D1, which will act as a refresher, make sure that there's nothing you've missed so you're ready to start the exam questions. Okay, now the central tenet of D1 is to understand what an algorithm is and to see different algorithms and how they're used and what their purposes are. So what is an algorithm? It's a set of precisely defined instructions. It will work for all valid inputs. It's finite, so it has a stopping condition. It could be an iterative process, which means you need to perform a step or a calculation a certain number of times until you get close to an acceptable solution. Okay, so let's have a look. Bin packing algorithms. Now these are heuristic algorithms. It means that this algorithm won't find the best solution, won't necessarily find the best solution, but it generally leads you towards a good solution. The three algorithms we're going to look at: full bin packing, first fit, and first fit decreasing. They go from being something which is computationally quite taxing in terms of the full bin packing to something that is not so taxing, the first fit, and then the middle ground, the first fit decreasing, which requires a little bit of computation but gives generally an acceptable solution. It's kind of like the middle ground. So let's have a look at full bin packing first. So we have our numbers and they have a specific order and we're going to apply them. So first thing you need to understand is how do we apply these numbers and what is our first number. So our first number in this row is 0.5. So it might be easier to kind of envisage that these numbers are approaching on kind of like a belt. They're gonna go and fill the first bin, and then when that's filled, they'll move on to the second one and the third bin, and that's how they're going in. So once you understand that, you know that the first number that you're applying is the 0.5. Each bin has in this case has a size of 1. So you put your 0.5 in, and you cross it off. Then you have 0.7. Again, you try it in the first bin, it won't fit, it goes over the top. So we put 0.7 in the second bin. If you put it anywhere else, it's wrong. 0.5, we try the first bin, it does fit. So this is kind of the process we're looking at for putting it in. Now, the particular process we're looking at here is full bin packing. So full bin packing, what it does is it looks at all of these values and says, actually, we're not gonna do that. We're gonna use our brains and we're gonna look at the pairings of numbers and try and make the number 1. So our first 0.5 and 0.5, it works, it's a 1. What about 0.7? There isn't 0.3, but there is a 0.7, 0.2, and a 0.1. So we have another full bin. That's why it's called full bin packing. So 0.7, 0.2, 0.1. Okay. Anything else? Well, the 5, there isn't a 5, but the 4 can go with a 6. So 0.4, 0.6, leaving us with 0.5 and 0.2. So these bins are all full. They are full to the brim. They have exactly 1 in, and this last one has a gap of 0.3 at the top. So that's a pretty efficient solution given our numbers, but that takes a fair amount of, it might be easy for us to do, but that's only because we're only dealing with a small amount of numbers. Imagine we were dealing with 50 numbers or 100, and how long would that take? So the idea of this is to take an algorithm that can be applied to a small group and develop using a small group, and then you can apply it to larger problems. Okay, next one is the first fit. So this is kind of close to what I was talking about before, where you put it in the first available. So our first available here is 0.5. The first available for 0.7 can't go in here, goes in here. And then 0.5, this is the first available. 0.2 can go in here, so we're getting close to a similar solution. 0.4, well, this is full now. 0.4 will go in here. 0.2, 0.9, no, can't do that, but it can go here. 0.5 can't go in there, can't go in there, so it must go here. 0.1, we have a full bin, we're good. And finally 0.6, well, 0.6 can't go in here, and 0.6 can't go in here. So for this solution, it's less optimal than our full bin packing. Our full bin packing, we managed to find a perfect solution with 4 bins. Whereas here, for this solution with the full fit, first fit, we require 5 bins. Not so good. Now let's look at the first fit decreasing. So for the first fit decreasing, we take our numbers and we put them in decreasing order, and doing the same thing. We start applying from largest to smallest. So 0.7 now goes in the first bin. Cross it off. 0.6 won't fit in the first bin, so we stick it in the second. 0.5 won't fit in either of those, so it goes in the third. 0.5 won't fit in the first two, but it will fit here, and our bin is complete. 0.5 goes in here. 0.4 can go in our second bin, which now is complete. 0.2 and 0.1. So that gives us an answer which something feels wrong. There were 2 0.2s. Dun, dun, dun. Let's ignore that one. That never happened. You can't prove it. Okay, right. So I failed to cross off a number 2. So what's the lesson? Cross off what you're doing exactly. Okay. So we have 3 full bins and a 0.5 extra, which gives us an ideal or perfect solution. You know, we're full bin packing, but without using a full bin packing algorithm. So the first fit decreasing gave us an acceptable solution, or a comparable solution, identical solution to full bin packing, but it's something which computationally is quite easy. All we need to do is find an algorithm that will arrange numbers in order, increasing or decreasing. I wonder if we know what one of those is. Okay. So hang on a minute. Okay. So algorithms have a certain structure. This is an algorithm kind of like graph, and it has various stages to it. Each of these boxes has a certain purpose. The rectangular box indicates an action. A diamond-shaped box or a rhombus indicates a question or a choice. So we have our algorithm, and the question says, what's the output of the algorithm when you use 84 and 660 for A and B? So we set up a table. So we have A and we have B. And what are the other variables in our question? Well, we're going to have Q, we're going to have R1, and we have R2. So we work on this step by step. So we're only looking at this column now. We know A is 84, we know B is 660. Q is the integer value of B divided by A. So B divided by A will be 7 point something, so we're going to write it as an integer 7. And what is R1? B is the remainder of A times B, A times Q, so 7 times 84, subtracted from 660, which gives you a remainder of 72. Okay, now what happens in our next stage of calculation? Let B equal A, so store A in B. Our A value is 84, so therefore we store this value, so this gets written in. A equal R1, so our R1 value is currently 72, so that goes here. Then we do the division, 84 over 72, well that's going to be 1 point something, so we write 1 here. Now, how do we find R2? Well, it's B minus A times Q. So 84 minus 1 times 72 is 12. And we're continually checking that R2, is it greater than 0? In this case, it is. Now we go back and we start from the top again. Let's store our B value in A. Sorry, our A value in B. Yep. So 72 goes here. Let A equal R1. Our R1 value. Let R1 equal R2. So there should have been a 12 here, and we store that over here. So let R1 equal R2. We have our 72. And then we divide them. 72 divided by 12 is 6. Okay. Now let R2 equal B minus AQ. So 72 minus 6 times 12 is 0. Is R2 greater than 0? The answer is no. Print R1. So our R1 value is 12, so we print 12. So it's an iterative process. We're going round and round until we hit a certain condition. Our start condition is R2 being less than or equal to 0. And what does it do? Well, it finds the highest common factor of A and B. It might not be obvious, but if you're not sure, there's nothing to stop you doing it yourself. So with your own choice of number. So let's say, how would that work? Let's say we were working on let's say we were working on 12 and 20. So we know that the highest common factor of 12 and 20 is 4. So let's see what we get. Going through the steps. Q is B over A, so B over A is 12 over 20, so that's going to be 1. And 20 minus 1 times 12 is 8. Okay? Now we let our B value equal our A value, so that's 12. And we store our R1 here, and we divide, and we get 1. Okay, and 12 minus 1 times 8, and we store that in R2. And we get, so we notice that we're storing that in R2, and that's going to give us 12 minus 8 times 1, which is 4. Okay, so let's go. Let R1 equal R2, so that goes here, so we write R4. That's this step here. Now going back around, let B equal A. Let A equal R1. Let B equal A. Let A equal R1. So it's going to be 4. And 8 divided by 4 is 2. And our R2 value is going to be 8 minus 2 times 4. So 8 minus 8 is 0, which is when we stop and we print our R1 value, which is print 4. Which is the HCF. So this is a program algorithm that would work it out. And you can code this, and this is how, for example, features on calculators work. When you ask a calculator to find the LCF HCF or the LCM of a pair of numbers, how does it know? And it follows a set of instructions similar to this. It follows the steps of the algorithm, it gets an answer, and it outputs it. Okay. So in the previous example, I talked about the first fit decreasing. The first fit decreasing requires sorting the numbers, in that case in descending order. We have two algorithms that we talk about for sorting numbers into order. There's the bubble sort and the quick sort. So the bubble sort works by comparing pairs of numbers and rearranging them based on let's grab these numbers from here. Rearranging them based on a direct comparison between two numbers. The quick sort is a little bit more colorful, and the quick sort uses an algorithm to repeatedly split our group into pairs and compare into halves, and then compare the halves. Okay. So normally the standard format for bubble sort is you would be asked to explain each step of a pass, and once you've done that, you might be asked to just do the end steps of the pass. So I'm going to go through what is involved in the first pass. Okay, so we will compare our first two numbers, which are 0.5 and 0.7, and let's say we want to go descending, so we want our biggest number on the left. So comparing 0.5 and 0.7, do we switch? We do. So we write 0.7, and we don't write 0.5, so 0.5 is here. We're going to compare 0.5 with 0.5. No one is stronger than the other. Now we're comparing 0.5 and 0.2. Also going down already, we don't need to change. 0.2 and 0.4, we're going up, so we need to switch. And then 0.2 and 0.2, no direct change. 0.2 and 0.5, we need to switch. So it'll be 0.5, 0.2, 0.2, 0.1 are going down, so that's fine. And 0.1, 0.6 will need to switch. Okay, so that's one pass through our values. So we look at the switches we made. We made a first switch here. We made our second switch here. A third switch here, and a fourth. So we made 4 swaps in that pass. And then we repeat this until we get a pass in which no swaps are made. So what you find with each pass is the smallest number will move to the end when you're doing descending. If you're doing ascending, the biggest number would move to the end. So, and on the next pass, we can ignore the 0.1 because 0.1 is the smallest number and it's already in the correct place. So let's apply again. 0.7 is fine. We're going down. 0.5 is the same, so don't need to change. 0.5 to 0.4, already going down, no need to change. 0.4 to 0.2, no need to change. 0.2 to 0.5, we do need to switch. 0.2 to 0.2, no need to change. 0.2 to 0.6, we do need to swap. So we had a swap here, and we had a swap over here. And that will give us a 0.2 with 0.1. Okay? So you can say these are already in order. So the only swap you would get on the next one so 0.5 would be 0.5 would switch with 0.4, 0.2 would switch with 0.6, now if you look at this, we're almost in perfect order. The only thing that needs to move is the 0.6, and each pass will move it once. So on the first pass it will go here, on the second pass, third pass, fourth pass. So there'll be 4 more passes before we get to 0.7, 0.6, 0.5, 0.5, 0.5, 0.4, 0.2, 0.2, 0.1. And that is the bubble sort. If you complete the pass again and you see there are no swaps, and that means you can terminate. Given that after each pass, at least one number will be in the right place. So in this case, after the first pass, 0.1 was in the right place. After the second pass, 0.2 was in 0.2 was in the right place. After the third pass, the second 0.2 was in the right place, and so on. And given that we have 9 numbers, that means the maximum number of passes will be 9. So if you had a perfectly bad arrangement of numbers, in that if you had 0.1, 0.2, 0.2, 0.4, 0.5 times 3, 0.6, 0.7. So the opposite of decreasing. If they were in perfectly increasing order, that is the worst possible starting point. But there are 9 numbers, which means the maximum number of passes is 9. Okay? So what's the maximum number of swaps? Well, if we have, let me write this out. If we had a swap at every stage, we'd have 1, 2, 3, 4, 5, 6, 7, 8 swaps. So if there were 9 numbers, we'd have a maximum of 8 swaps. If there were 8 numbers, because after that there will only be 8, it would be 7 swaps. That means that if I gave you a list of 7 numbers and said what is the maximum number of swaps, well, if it's 7, then there will be 6, then there will be 6 numbers in the next row, which will be 5 swaps, 4, 3, 2, 1. So that's going to be 15, 21. So 21 swaps will be the maximum number of swaps. And that's another thing that you can be asked. And it's good to know that. Hang on, let me just restart. Okay, quick sort. Now this one's pretty. It's got lovely shapes. We're going to have some triangles. We're going to have some squares. We're going to have some circles. We're going to have so much fun. Okay. Let's see. Do we have the numbers from before? We do. And so if you have 9 numbers, you need to pick the middle. And the middle is a half of 9 rounded down. So half of 9 is 4.5, rounded up, which gives us 5. If you have 10 numbers, you pick the halfway point, which is 5, and then you, so the halfway point will be, so if you imagine 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have our 10 numbers, and our middle point is here, but what's our middle number? Well, it could be 5 or 6. By convention, when we have an even number, we go to the next highest value and just consistently do that. So half of 10 is 5, round it up, 6. Okay, so that means our middle value will be 6. Okay, so we have 5 and we have 6 depending on how many numbers we have. So let's have a look at our numbers. We have 3, 6, 9 numbers. So our middle value will be our 5th number. Let's put a little square around it. And then we're comparing each number to our middle value. So we've got our square around our middle value. And then we're looking at 0.5. Is it bigger or smaller? So are we choosing to do this in descending order? If we are putting it in descending order, then we want small. So I'm going to write this here. Big numbers on the left and small numbers on the right. I'm just going to write that to remind me, because otherwise I get confused. You know me, I'm getting old. All right, so we start 0.5. Yes, that is big compared to 0.4. Then 0.7. We are not doing any sorting at this point. So you're not using your brain. You are automating this process. I'm just going to give myself a little bit more room. Yeah, you should be able to teach a computer this, which means it shouldn't have to think for itself. So 0.5, 0.7, 0.5, that's on the big side. 0.2, that's on the small. 0.2 on the small. 0.5, that's on the big. 0.1, 0.6. This is the only correct solution. If any of your numbers are not in this specific order, your answer will be considered incorrect. Now we look at our groups either side of 0.4 and we pick a middle point. So here we have 3 numbers, so the middle one is 0.2. Here we have 5 numbers, so our middle value is 0.5. So now we compare in each half, put our placeholders down. So 0.5 to 0.5, well, it can stay where it is. 0.7 to 0.5, that's on the big. 0.5 can stay because it's the same. 0.5, that can stay where it is because it's on the small, doesn't need to move. 0.6, oh, that's on the big side. I didn't give myself enough room. And that's okay. It's okay to erase and reassign and give yourself enough space. So we have our 4 numbers sorted. Now the 0.2, since it's equal, it can stay where it is, and 0.1 stays where it is. It's on the small side. So now I'm going to use some inverted triangles on each of these numbers in the gaps. Anything that's kind of like got a shape around it, it means it's completed. So 0.1, 0.2, 0.2, 0.4, 0.5, 0.5, and we're going to have 0.7. Okay, so let's sort around the 0.7. 0.5, bigger or smaller? Smaller, so it goes on the right. And 0.6, smaller, it goes on the right. Okay, so then we look at our group and pick the middle value. Remember, if there's 2, half it and round up. We do this. Our sort will put 0.5 on the other side, which will result in our fully sorted in descending order set of numbers. So go back, review, rewind, make sure you understand everything about this. Try it with your own set of numbers as well. Okay, well done. Thank you very much.